So we started this on Friday. Using properties of logarithms. Our product property stated that if two or more things are multiplied together inside of a logarithm, we can rewrite it as a sum of two logs. Quotient property says if we have two things being divided inside of a logarithm, we can rewrite it as a difference of two logarithms. And our power property says if there's an exponent, we can move it to the front. And we're going to use those properties to approximate the value of each one of these here. Because the first one is log base 2 of 3/7. Now they told us what log base 2 of 3 is. It's 1.585. And they also told us what log base 2 of 7 is. It's 2.807. And we can use these two values to approximate what log base 2 of 3/7 is. Because according to the quotient property, we can rewrite this as log base 2 of 3 minus log base 2 of 7. Quotient property says if we have two things being divided inside of a logarithm, we can rewrite it as two logs being subtracted. It is. Now they told us log base 2 of 3 is 1.585. And we're going to subtract from it log base 2 of 7, which is 2.807. Now we just need to subtract these two here. 1.585 minus 2.807. Which is negative 1.222. Questions on the first one? First one's kind of nice, 3/7. It kind of told us what we need to do. Now the second one, log base 2 of 21. Can we rewrite 21 using 3 and or 7 using multiplication, division, or powers? Multiplication, it's what? 7 times 3, 3 times 7. So we can rewrite 21 using this product. And according to our product property, this is the same as log base 2 of 7 plus log base 2 of 3. And according to what they told us, log base 2 of 7 is 2.807. And log base 2 of 3 is 1.585. And now we just need to add those two together, because once we add those two approximations together, we figure out what log base 2 of 21 is. And it tells us it's 4.392. Questions on either one of these here? Let's look at the last one here. How can we rewrite 49 using multiplication, division, or powers with 3 or 7? 7 times 7 is 49, or 7 squared if we want to use exponents. because 7 times 7 is indeed 49, so 7 squared. And according to our power property, we can take that exponent and move it to the front, which is telling us that we have 2 times log base 2 of 7. Well, log base 2 of 7 is 2.807. So what we're saying is that we have 2 times 2.807 because we can replace log base 2 of 7 with its approximate value. And then we just need to multiply this by 2. And we can do that in a calculator. 2.807 times 2 is 5.614. So its approximate value is 5.614. Questions on this here? Now, for the most part, this doesn't help. I mean, it's good to know and good to understand how we do this. But with graphing calculators and being able to calculate log base, and we'll see another way to calculate it, and with calculators being able to do this, it becomes less meaningful because it can do it for us. But when we didn't have calculators with a strong enough power to be able to just calculate these values, we needed ways to evaluate it and solve for it from a limited set of known values. So let's look at 3 more of these here. It tells us that log base 3 of 4 is 1.262 and log base 3 of 5 is 1.465. And we're going to use those to evaluate each one of these here. Now, A is kind of nice because it's log base 3 of 4/5. It's already told us how we can interact with 4 and 5. So really this is the same as log base 3 of 4 minus log base 3 of 5. And the top number will always go inside the logarithm first. We'll always have log at the top minus log of the bottom. And according to what they told us, log base 3 of 4 is approximately 1.262. And log base 3 of 5 is approximately 1.465. So now all we need to do is subtract these two, 1.262 from 1.465. Negative 0.203. Questions on A? B, log base 3 of 20. Using 4 and 5, how can we rewrite 20? So it'd be 4 times 5, yes.
I have a question.
Yes.
I don't if the log base is like that. So the last equation you did, log base 2 and log base 3, is different? There's no difference?
Well, the big difference between log base 2 and log base 3 is the value that we're looking for. So log base 3, what it's saying, and kind of if we're trying to find the value of this, 3 to what power is 20? That's really what we're trying to find. Now, in the previous ones, where it's saying log base 2, it's saying 2 to what power is 3, 2 to what power is 7. So essentially, they are different in the fact of what we're trying to find. Now, specifically why they picked 2 and 3, I don't know. They decided for these problem sets to use 2 and 3. But the number itself has meaning in what we're finding. That's why here, log base 3 of 4, 1.262, is smaller than log base 2 of almost this, well, log base 2 of 4 would be 2. Because it seems like log base 2 of 3 is 1.5. Log base 3 of 4 is 1.26. Numbers went down, but it got smaller. That's really how it looks. Does that make sense? Okay. And the reason that we do this here and then rewrite this is because most likely we would have, say, for log base 3, we would have the first so many numbers, 10, 20, but they wouldn't have everything. So these properties give us a way to use those tables to still find values without having to find the value of everything and put it in a table. To where we can rewrite log base 3 of 20 as 4 times 5, log base 3 of 4 times 5, which is log base 3 of 4 plus log base 3 of 5. So we're adding 1.262 to 1.465, 1.262 plus 1.465, and we get 2.727. But especially with graphing calculators being able to go math, log base 3 of 20, 2.7268, it will do it for us. 727, so it did round to that third decimal place, we got the same thing. So before we had calculators that can do this easily and effectively, this was the best way to solve it. But now that we have calculators that I can plug log base 325 in and get the answer, it doesn't serve a whole lot of purpose. It does help us find this and use the properties, but that's about it. Yeah, 5 times 5 or 5 squared, and it gives us the same thing, funny enough. The nice thing with 5 squared is we just take that 2 and throw it to the front. 2 times log base 3 of 5. Log base 3 of 5 is told to us to be 1.465, which would be 0, 3, 9, should be 2.30. We can throw it in the calculator and tell it, multiply those two out. Same thing. Questions on this here? You're good. Now the next property is actually very helpful, and it's called the change of base. Change of base. Log base b of m is equal to log of m over log of b, which is actually equal to the natural log of m over the natural log of b. And according to the change of base formula here, we can change the base to whatever we want it to be. So the new logarithm, log base c of a, is equal to log of b, log base b of a over log base b of c. Now for the most part, we change that value, that base, we're going to change it to 10. That's common logs. The calculator can do common logs. We can just do log of that over log of that. It types it in nicer. And if we wanted to, we could also change that base to e. When the base is e, it's natural logs. So, as I've always said, seeing the definition and seeing how it works, I think it becomes a little more helpful, a little more useful. Because if we're looking at this first one here, log base 3 of 8, if we wanted to type this in at this point, we'd get the graphing calculator out, go math, down to log base, type it in. According to the change of base theorem, I can change this from log base 3 of 8 to log of the top, or log of what's inside on top. So that'd be log of 8 over log of the base, which is log of 3. Because what we've done is change the base to 10. And I can come over here in the graphing calculator, do the same thing. So we find out what it is originally. So we're looking for log base 3 of 8, and it tells me it's this here. But according to the change of base theorem, this should be the same as log of 8 divided by log of 3. And it is, and it has that same value, which means with these logarithms that don't have a base of 10, I can use this change of base theorem and plug them in either one. Because that means now, even in the 30xs, I can go log of 8 over log of 3, and it gives me the correct answer. That's nice. We're not having to type all that in. Interestingly enough, natural log of 8 over the natural log of 3 is still the exact same value. So this is the same as the natural log of 8 over the natural log of 3, which is approximately 1.893. Questions on this here? How would we rewrite log base 7 of 11 using common logs? It would be whatever what? Log of 11 over log of 7. If I wanted natural logs, it'd be the natural log of what? 11 over the natural log of 7. Yeah, we had 3 on the last one. But that's it. Natural log of 11 over natural log of 7. Or log of 11 over log of 7. Which means I can grab the calculator and say log of 11 over log of 7 and see that it's 1.232. Yes. So natural log of 11 over the natural log of 7. So when we want to evaluate log base 7 of 11 and I don't have a calculator that can do that log base, instead of trying to work it out and find it out, I can say log of 11 over log of 7. It gives me more options. Because this also means, especially when we looked at that table on Friday where it had that set list, I don't have to have log base 7 of all these numbers. As long as I have the base as 10, this change of base says I can use that to figure out all the values. So a lot of these here and a lot of these methods, it seems very arbitrary. It doesn't make sense in our current day and age because we have so much technology that can do it for us. So before we had that, we needed ways to figure it out and calculate it with as little resources as possible, or what we had. So if we just had a table of logarithms in base 10, if I have ways to get it to base 10, I now have ways to calculate all of them. And that's the nice thing. So if I wanted to evaluate log base 6 of 24 and I did not have base 6 charts, but I had base 10, I can convert it to it. And we can change this from log base 6 of 24 to log of 24, what's inside, over log of the base, which is the same as the natural log of 24 over the natural log of 6. And luckily for us, we don't have a chart that we have to reference and look up. Log of 24 over log of 6 is 1.774. Questions on this here? Questions on any of this so far? Evaluate log base 2 of 19. If we rewrote this as common logs, how would this go? We'd have log of what over log of what? Log of 19 over log of 2, which is the same as the natural log of over the natural log of 2. Okay. So we're going to calculate this. I'm going to approximate this. So we're looking for 2 to what power is 19? 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. So 2 to the fourth was 16, yes? 19 is bigger than it. So we're saying 2 to what power is 19? I know 2 to the fourth gave me 16, yes? Is it closer to 16 or 32? 16. So what I'm assuming is the first number is going to have to be 4 point some number is going to be closer to 4 than it is 5. Because if we were looking at log base 2 of 30, 2 to the fifth is 32, so we should have a number close to 5.
What's the difference between the common logarithms and the natural logarithms?
The base. The difference between the common logs and the natural logs is the base. Common logs, log is base 10. Natural logs is base e. And that's the only real difference between the two. So we have log of 19 over log of 2, which is 4.27 or 4.248. So we could, if we wanted to, use log base and say log base e of a number, and it'd be the same as taking the natural log. Questions on these here? Do we need to see another example of using change of base? That's it.